Yeah. So yesterday we discussed about the Petrov's equation. Today we are going to discuss further. We are going to continue this our journal bearing remaining concept. Okay. Okay. Now yesterday we discussed this on Petrov's equations to define the coefficient of friction in the bearing. Right. Now today we are going to discuss about this McKay's investigation. So what has been found in this in his research work that finally we are using this concept in our design of the bearing. Okay. Now see here in hydrodynamic bearing, initially the journal is at rest condition. When the journal is rest condition, the journal is touching on the surface of the bearing. I would like to show you this video. 1 minute. Okay. Are you able to see this video? It's not working, I think. This is only okay. Now I do one thing. I take this video, I copy and paste it. You can see this. Now, when this, are you able to see my screen? Yeah. Are you able to see my screen? Sorry. Hello. Okay, come out. Stop sharing. Now I go to sharing for my website. This is yeah. This is the see here the hydrodynamic bearing. Initially it rest at rest that the bearing is rest. Okay, when the journal is rest without rotation, then the journal is contact with the bearing surface. When it starts rotates, when it starts to rotate, climb to rotate, what will happen? Initially, therefore, the metal to metal contact surface. Then the journal starts to rotate. It takes some time. It takes some time for obtaining the hydrodynamic film. Hydrodynamic film. Why? Hydrodynamic film means to build up a sufficient pressure, to need some time to build up a hydrodynamic pressure inside the fluid to separate the journal and the shaft with hydrodynamic lubrication. Hydrodynamic lubrication in that sense, to make a thick film between the journal and bearing. Because that's what initially it will take time that to develop that pressure. Initially it takes some rotation. After it will be developed that hydrodynamic lubrication. Thick film will be developed due to pressure created between the journal and bearing with the help of the lubrication. Lubrication. see here, see here. You able to see here. This is now see here. Are you able to see my video? Are you able to see this video, please? Hello, guys. Are you able to see this video?
Yes, sir.
Okay. Now see here. Slowly it will start. I keep it here now. Now, your rest conditions, means looks like boundary lubrication. Now, when the journalist starts to rotate, then slowly the pressure is fluid pressure is developed inside the journal. Between the journal and bearing. Okay. now, Now, as the speed increases, now I tell you, as the speed increases, more and more lubrications entered. More and more lubrication are forced in between the journal and bearing to make the wedge shape clearance. Wedge shape thickness, this is also called thick film lubrication. Okay. I mean, the clearance space, now the clearance space and sufficient pressure is built, then the bearing and journal are separated. Securely, bearing and journal are separated. Now, smoothly, the power is going to be transmitted. Now, here some transition going to happen. That transition we are going to understand now. That is a very important thing. What is that transition? Transition in that sense. See here, initially rest condition, boundary lubrication, and when the speed increases, the boundary lubrication going to be a thick film lubrication. Lubrication is nothing but the hydrodynamic lubrication. Okay, now the transition, how it is happening, we are going to understand through the graphical method. Through the graph, because already the guy did experiment. The Mekis brothers did experiment and they plotted. Now we are using that the curve to understand this, how the transition is happening while the journal is rotating from rest condition to full speed. Because transition means here from bound lubrication to thick film lubrication. The transition, how it is happening. This guy explained while changing speed of the journal. Okay, now I stop sharing. I go to my slide now. That's what. Now see here. This is a concept. Now, this is also called the transition from thin film lubrication to the transition from, I mean, thin film lubrication to thick film hydrodynamic lubrication can be a better, it will be better visualization with the help of the, it can be a better visualization with the help of the curve. That is, curve is called mu NP curve or bearing characteristic curve. Now see here, he has been plotted that the coefficient of friction versus bearing characteristic number. This is, characteristic number, this is unitless. Okay, unitless. Now, see here, this is the transition from thin film lubrication to thick film hydrodynamic lubrication can be better visualized through this curve. Now see here, this is the mu is absolute. What is the notation he has been? You have to understand mu is nothing but viscosity of the lubricant, is speed of the journal, and P is the bearing pressure, load per unit area. I mean load per projected area. Sorry, load per projected area of the bearing. This is the new terminology used here. The bearing modulus. Now, how we consider bearing models? Now, see here from this plot. I mean, this is the plot. He obtained the data from the laboratory and he plotted. While the journal is coming from, rotating from rest condition to full speed condition. How the thin film to thick film, transition happened. Now there are two distinct parts here, B and C, right? Very simple. This is not difficult one. B and C, the region B and C. Okay, I take my pen. The region B and C is the partial metal to metal contact. The region B and C is the partial metal to metal contact and the patches of the lubricant. Here, this is the condition of thin film lubrication. B and C is the thin film lubrication. This condition is unstable. In this now, during this time, our bearing system, it's unstable. Unstable means not mechanical equilibrium, because unstable in that sense. What is unstable here? Now this is a bad journal. Sorry, this is a bearing surface fixed. Okay, this is a journal. Unstable means it's moving, keep on moving in y direction. The journal is moving to y direction from rest condition to rest, from the rest. I mean, when the journal is rest condition, it will be touching on the surface of the journal. Bearing. When the rotation going to happen, then slowly moving to center of the bearing. Then this is unstable. This is not a mechanical equilibrium. Once the thick film lubrication going to happen, then the journal is going to be stable rotation without oscillation. It will be a stable rotation able to obtain. That's what we are saying. Now this is the consideration of thin film and thick film lubrication, thick film boundary lubrication. Okay. Now the line CD is the thick film lubrication, also called hydrodynamic lubrication takes place. The AC is a dividing line. Now this is the modes of lubrication. Now what we have to understand here, some of the standard values we have to use in our design condition. Now see here, the coefficient of friction is minimum at C. The coefficient of friction is minimum at C. The bearing should not be preferred near this critical value. Near the critical value of K, this is nothing but our bearing modulus. This is bearing modulus at point C. Now slight drop in mu n p divided by mu n by p. Sorry, mu n by p. Slight drop in speed, slight increase in bearing pressure. Also, it will be reducing our. It will be leads to boundary lubrication. Boundary lubrication. So, what are the guidelines to be followed while defining the bearing modulus? We have to follow some guidelines to understand and to define bearing modulus, or define our bearing characteristic number. Bearing characteristic number is nothing but mu n by p. Very important for bearing manufacturing companies. Okay. Now, what are the guidelines we should follow here? See here, in order to avoid the seizure, the operating value of bearing characteristic number mu n by p should be at least 5. At least 5. This is they studied well. That's what they're telling. At least 5 to 6 times of the coefficient of friction is minimum. Means that 5 times of bearing modulus or 6 times of bearing modulus should be followed for our bearing design. Okay. Now, if the bearing is subjected to fluctuating load and or impact condition, then during that time we should follow our bearing characteristic number 15K to 15 times of modulus, bearing modulus we should follow. Okay. Whenever we are using for fluctuating and impact load condition. Okay. Now, I mean, it's here, see here, it's observed from that mu and p curve, the viscosity of the lubricant is very low. Viscosity of the lubricant is very low when the value of mu and p, the mu and p parameter will be low, because and that leads to boundary lubrication. When the mu n p value, bearing characteristic number value, or mu n by p value is less, that leads to boundary lubrication, then it will be more wear and tear going to happen in our journal and bearing surface. Hence that we have to avoid that issue. Okay, so we have to always take higher bearing characteristic number. Okay, now that's what we are telling here. Now I come to the hydrodynamic lubrication. Now, early we discussed the Petrov's equation to define the coefficient of friction. But now we are going to discuss about hydrodynamic lubrication behavior. We never, actually we didn't discuss that. Only we discussed coefficient of friction. Next case, Mekis told that, I mean, what is the bearing characteristic number and how to define, I mean, the transition state from thin film to thick film, how it is happening. Then based on that information, what is the bearing modulus we should follow in this concept. But now we never studied about behavior of the hydrodynamic lubrication. Now we are going to discuss about that. The hydrodynamic lubrication is defined based on that differential equation. The hydrodynamic lubrication was, defined based on differential equation. That equation developed by Reynolds, O. Reynolds. That guy who developed that concept, O. Reynolds. Hence, we are saying that Reynolds equation. Because now we would like to understand our hydrodynamic lubrication behavior. That thick film lubrication behavior, how it is. Okay. Now, while he developed his concept, he assumed some of the assumptions. Few assumptions he considered for developing his concept. Okay. First assumption: lubrication must obey the Newton's law of viscosity. The lubricant must be incompressible. The inertia force must be neglected, right? The viscosity value of the lubricant must be constant, right? The effect of curvature of the film, with respect to thick film, is neglected. The curvature of the film effect should be neglected. The curvature of the film, this curvature of the film is very thin film. This is the thick film as compared to this film curvature effect, thick and thin film curvature effect neglected, and it assumed that the film is so thin. When the film is so thin, the pressure is a constant across the film thickness. He says that each layer of fluid, the film, the pressure is constant. The bearing pressure is constant, he said. And the shaft and bearings are rigid. Now there is a, now see here, now in this concept we are continuously supply the lubricant. Why we are continuously supply the lubricant? Now to observe the heat, because he considered viscosity is a constant. Suppose we are not supplying the continuous lubricant, the present lubricant is going to be heated, then temperature will be rise. Temperature will rise, obviously viscosity going to be decreased. That's what he is saying, that there is a continuous supply of lubrication. Due to continuous supply of lubrication, then we will be able to avoid this change in temperature. now in this concept, this is the, whatever we discussed, journal bearing front view. This is a cross-sectional view of the bearing, right? Now this is the cross-sectional view of the journal or shaft. Now this is our fluid or lubricant. So this is our lubricant. Now in this lubricant, now sorry, lubricant. Now this is the load W is acting on the journal. N is nothing but our speed of the journal or speed of the shaft. Now in this, now we are in XY plane view. XY plane view. Now, now he considered a small fluid element. In that fluid element is here. This is the small fluid element. This is small fluid element. He considered in his work. The fluid element volume he considered dimension dx, dy, dz. The fluid element dimension. Okay. Now this is, direction of rotation. Okay, speed. This is the direction of rotation. Now, in the xy directions, the fluid element velocity u, v, w respectively. The velocity in the x, y, z direction, the fluid element velocity is u, v, w respectively. He considered the notation like this. Now see here, now where he considered the fluid element, then corresponding, where he considered the fluid element here, corresponding fluid film thickness, clearance, he considered h. This is the clearance. Clearance between the clearance is nothing but the distance between the journal and bearing. How much fluid occupied, that thickness is, that dimension is called h. H is nothing but a clearance. He considered in his notation h. Now, one by one we are going to discuss now what is the fluid element viscosity, velocity, fluid element velocity with respect to x direction, with respect to z direction, with respect to y direction. Then once we obtained that equations, we able to characterize, we able to understand, or we able to understand the behavior of the hydrodynamic thick film lubrication at each direction. What is the velocity? Because while rotating this shaft, the fluid also moves, right? We would like to understand, because we know that, we know this is velocity of the shaft, but we don't know characteristics of this fluid film. That's what we would like to understand, the fluid behavior with the help of his Reynolds concept. So hence now we have been understood that x, v, u, v, w, what it is, and also we have been considered small fluid element. Now this is in xy plane. Now this is in the now this is in yz plane. Yz plane is nothing but this is extension of that yz plane. Okay, in the yz plane should be here, where this is the hole for oil hole for continuous supply the oil through this hole. Now come to this this is the xy plane. Now come to this yz plane. Yz plane, this is our shaft, this is our oil hole, this is a bearing. I take my, this is our bearing, this is our oil hole, this is shaft, this is the diameter of the shaft, this is now y direction, this is z direction. Now this is our fluid element. Which one is we are concentrating in our evaluation, in our derivation? This is a fluid element we consider. Now this is in y z plane view. YZ plane view. Now please understand here. Now while this I'd like to erase many of the things, then only you can easily understand. Now the shaft is rotating in this direction, right? What will happen? This fluid element is here. Now whatever we assumed fluid element is here, right? Now what will happen? When the shaft rotates this direction, now this region subjected into normal pressure or shear load. This region, please someone reflect. This region and this region. Now I'm talking about this region now. This region, this surface. Now this surface, the purple color, this surface. Now you tell me that now where I am pointing out this region is normal pressure or it's shear behavior, shear load acting in the fluid element while rotating the shaft in this direction. Is it normal load or shear load in this place? I draw it separately here. This is a fluid element I considered, right? Now this region subjected to normal pressure or shear load. The same fluid element I have drawn here. Now what type of load here? Now this is what type of load here? Please someone reflect. Now I am considering this is A. This region is B. The region A subjected to normal load or shear load? Please tell me. This region subjected to normal or shear? Hello? Yeah, Ansari. Jayesh. Amarnath. One-way communication not good, pa. Please, someone reflect. Hello?
It's shear, sir.
Yes. I mean, which region here? Region B or region A? Please tell me, man. Very simple. This is the journal rotation. Then this full fluid is moving like this. Whatever we assumed small elemental fluid. Now this region subjected to shear or normal pressure. The region A, the same region I have drawn here, then extended in 3 dimensional view. The region A is subject to normal load or normal pressure or shear pressure. You told shear, which region, ma? B or A? The region B or A shear. Guys, please don't delay. Hello. Without
A is shear, sir.
A is here. A is normal. See here, this is this. I mean, this is see here. 1 minute. Because this once you have understood this remaining derivation very simple. Now I am talking about this only. Now see here. Now this is a journal here, right? Now this is a top surface of the fluid. This is this view. Now I am asking this surface is shear or normal? That's what my question. And or else this surface shear or normal. But the fluid is now we are considering like this rotation, right? Now are you clear? Now the top surface is going to be shear. This surface, the blue color where I mean I highlighted that color is going to be normal. Are you clear or not clear? Hello.
Yes, sir, clear.
Okay, thank you. Okay, now I come to the concept. Once you have understood this, remaining things are very easy. This is a very big derivation. You may expect this type of questions even, I mean, public service exams. Even some students may try engineering service, right? Engineering service exams. Okay. Now I am considering this is XY plane. In the in the YZ plane. Okay. YZ plane now. See here. Yeah, the force acting on the element, now the force acting on the element in x direction, force acting on the element in x direction. Now considering the equating forces, now x direction, now x direction means here this is the element. Now in this element, now what is the force acting here? This is This is my element, fluid element. This is a dy. This is a dx. This is dz. Now, right, see here. I mean, this hidden region going to be subjected into normal pressure due to this fluid. Normal bearing pressure, P. Right hand side, P plus dou P by dou x into dou x into dx. Similarly, in bottom side here, tau. In top, tau x plus in top going to be tau x plus dou tau x by dou x dou y into dy because in y direction. Tau x plus dou tau x by dou y into dy. Now from this equilibrium of force condition, we would like to define equilibrium force. From this concept, we would like to find out the equilibrium forces. Okay. Now, now this is the P, normal force P. What is the area here? I mean, normal force P. Now from this relation, finally we are getting this equilibrium forces. Now, I mean, how we are getting this? That also I write it just 1 minute. Now, see here, P plus dou P by dou x into dx, right? Dx. What is this area? This area. This is the area, right? Normal pressure acting this area. I mean, dy into dz minus this load, this pressure, P into P, right? Now, the first simple manner we derive it. Minus P, later we multiply the area, doesn't matter. P, right? Is equal to, similarly, tau x plus dou tau x by dou tau x by dou y, because y direction, into dy minus tau x. From this relation, we can obtain the equilibrium force. Now this is x. P cancel, tau x cancel. Finally, we are getting this relation. Getting the relation, now this is in pressure. Now I am multiplying the area. I mean, this is going to be multiplied with area this side. Now dy into dz. This is multiplied with dy into dz. I mean, the shared area, this is shared area of the fluid element. Now that is dx into dz. Dx into dz multiplied by dx into dz. Okay. Now this is dx dy dz. Dx dy dz common. This is the volume of the fluid volume of the fluid element. We cannot consider 0. Then eliminate. Finally simplify this equation. Then substitute this. We already discussed what is a tau x. Tau x we already discussed in the, I mean, first class, I mean, the last class we discussed tau x is equal to mu into dou u by dou h. I mean, here we already discussed mu into dou u by dou h we discussed. Now on the left hand side, P by A. P by A is our shear stress. Now the dh is nothing but our y now. Instead of dh, I am putting dy. Now substitute this equation, we are getting, this is the equation. Dou squared u by dou y squared is equal to 1 by mu into dou p by dou x. Now this is the equation. From this second order partial differential equation, I able to find out my fluid velocity u with respect to x direction. See here. Now, I mean, this is a standard order differential equation, partial differential equation. Now integrate both sides, twice integrate, then we are going to get two unknowns. Then we have to apply the boundary condition to find out our velocity u with respect to x direction. Okay. Now 2 times integrate. Finally, we are getting this relation u is equal to 1 by mu into dou p by dou x into y squared divided by 2 plus c1 into y c plus c2. From this relation c1 c2 we do not know. Apply the boundary condition. When y equal to 0, u is equal to 0. When y is equal to h, u is equal to u. Apply the boundary condition and find out the c1 and the c2. Then finally a substitute in the same equation, u is equal to, we are able to find out u is equal to this. This is the fluid element velocity in with respect to x direction. Okay. Now second thing, now I mean we able, now we second case, sorry, second case we are going to consider now force acting in the z direction, force acting on the element in z direction. See, same thing, earlier case we have been considered y and z y and x axis. Now I'm taking, I mean y and z axis. Now I'm taking y and z axis here, y and z plane, z plane. Now what is this? This is a fluid element. Now this is a dz d, this is a dy, this is my dx. Whatever we discussed earlier, the fluid element with respect to xy plane. Now similar manner we discuss, we can consider, we can rewrite the, we can understand and we can say that equation dou square w by dou y squared is equal to 1 by mu into dou p by dou z. Whatever earlier concept, based on that we have been discussed, we have been derived this dou square w by dou y squared is equal to 1 by mu into dou p by dou z. Now this is also second order differential equation, again integrated twice. Then w is equal to, I mean 1 by mu dou p by dou z to y squared by 2 plus c1 c3y plus c4, because earlier I used c1 c2 here, so that confusion should not happen. Hence here c3 c4 I used a different constant notation, means c4 c3 and c4. Now you apply the boundary condition. Now the boundary condition here, this boundary condition we already know, even the last class we discussed. Now the boundary condition, w is equal to 0, y equal to 0. W is equal to 0, I mean when, sorry, when y is, this way I explain, when y is equal to 0, w is equal to 0. When y is equal to 0, w is equal to 0. When, okay, y is equal to h, w is equal to 0. I mean I come to this figure. See, this is the figure. Now you can consider for understanding how it is 0. Now I mean see here, this is the bearing in yz plane. Now this is the bearing in yz plane. In the yz plane, right, I mean the bearing is looks like closed. The bearing is looks like closed and no leakage. Hence when the bearing this surface y equal to 0, w is equal to 0 on this bearing surface and journal surface, with respect to z direction, the velocity of the fluid is 0, because both sides it looks like closed, right? Closed, it don't be a no leakage. But even though now, I mean, it looks like you might have been studied, the fluid layer is, middle of the layer is more velocity, and the boundary, at the boundary is going to be 0. The w is equal to 0 here, when w is equal to 0 here, when y equal to 0, when y is equal to h, with respect to z direction. Now what is this velocity, how it is changing? We would like to understand this behavior. Hence we want to describe, we want to derive this velocity with respect to z direction. Okay. Now come to this, I mean similar manner, substitute this boundary condition to define our, I mean velocity w with respect to the direction. Okay. Now I mean x direction we have found it, and w and w we have found it. Now we are going to concentrate v, small v. Okay. Now in v is, in the direction of v is, the fluid is stable, right? I mean not stable in that sense, incompressible. Oh sorry, now we are considering the fluid incompressible equation for deriving our velocity u direction, y direction, y direction. Now see here, this is they given the justification, despite there is no flow in y direction, the local continuity equations. Now this is the incompressible flow continuity equation. From this we are able to find out dv by dy is equal to minus from this incompressible continuity equation. From this dou v by dou y is equal to, from this equation only we have found this. Now I mean, now the integrating about this equation with respect to y, integrating with respect to y, because our variation going to happen. This is journal, this is a journal, this is journal, this is a bearing, right? Now in this, now this is a direction. What is this direction? I mean, this is a direction is y direction, right? We consider this is y direction. Where is, I mean, z direction? Z direction is, this is z direction, this is x direction. Now this is, now we are concentrating this only. Now we are concentrating this only now. Y. Okay. Now the y is nothing but y is equal to 0, y is equal to h. When here y is equal to 0, here when it will be y is equal to h. Now this is the limit I am considering, 0 to h. Now the given incompressible equation, now integrating 0 to h, both sides. Okay. Finally, see here the velocity also. Now what is the velocity? We already know that when y is equal to h, when y is equal to h, then v, u is equal to v. Sorry, I don't confuse here u, because u term we should not use. We are considering the velocity v. When y is equal to 0, y is equal to 0, velocity going to be 0. Velocity going to be 0. Now we prove it that. Now, I mean, now which view we consider? Now we consider this view only. Now we consider this view only. In this view, now see here that the journal moving from this, the point, while rotating journal, the journal is moving from this point to this point like this, right? Now, I mean, with respect to x direction, I can take, this is u, velocity u. When the journal moves from this point to this point, this point, this point, finally this point, I am considering v. Then this is the angle I am considering pi. What is the dimension here? The dimension is here. This is now the dimension dx. What is the dimension here? dh. Now this is h. Sorry, this is h now. This this is h, here to here h, but this is this from this dimension is dh I am considering. I exactly draw it now. From this, dh. Okay, from this point to this point is h. This point to this point is h, right? Okay, now this is u. I mean, from this relation we are able to find out what is the tan pi. From this relation, that's what he clearly told here. This is u, this is v. Okay, based on journal moment v, the dimension is dx and dh. From this we are able to find out what is a pi. What is pi? Okay, this is our film clearance height. Now, okay, now come to this. Now tan pi is equal to, now v by capital U, then dh by dx. Now finally v is equal to capital U into dh by dx. Now substitute this equation in this, substitute this equation, whatever we discussed in the equation O. Substitute this equation. Now this term is going to be 0. Only this term going to be, this term going to be v is equal to what? This term going to be dh by dx into u. Sorry, I write it here. Dh by dx into u. Okay, now this is our, this equation now, 0 to h, dou v by dou y into dy is equal to capital U into dh by dx. From this relation, now, I mean, what is our original equation? Our incompressible equation. In the y direction, we assumed that the fluid is incompressible, right? This is our original equation, where it is n. Substitute again n. Finally, we are getting this is equation. Okay. Now this is the equation. Now this equation we would like to derive. We would like to simplify, solve this equation using Lebesgue theorem. Lebesgue theorem. In this Lebesgue theorem, see here. I mean, there is two parameters are involved, x and y in the velocity u. Now, in the Lebesgue theorem, the Lebesgue theorem says that d by dh into lower integral h1 of x, higher integral h2 of x. I mean lower limit h1 of x, higher limit h2 of x is nothing but h1 of x nothing but h of x is equal to, I mean here h is equal to 0. I mean y is equal to 0. h2 of x is nothing but h. Okay, that's what I mean. This is a solution. This is a solution. D by dx integral of h1 of x into h2 of x, then u of x comma y into dy. This is the Leibniz theorem solution. The same solution. This is the solution obtained by the Leibniz theorem. Okay, Leibniz theorem. Now from this we are going to find out our solution for this with for our velocity v. Okay, now that's our h1 of x is equal to 0. Here y is equal to 0. h2 of x is nothing but h. Now when h2 of x is equal to h, u of x comma y, I am assuming that u. Okay, now I mean when u of y, please, this is very simple, it's not a difficult one. When h1 of x is when h1 of x is 0, h2 of x is equal to h, generic manner I am considering, u of x comma y I am considering small u. Now I apply this. When now I apply the boundary condition here, u of x comma y, here u of x comma y is nothing but this, y is nothing but h1 of x, h1 of x. Then during that time u is going to be 0. Now u of x comma h2 of x, this y is going to be now h2 of x. Then during that time u going to be capital U. So this is the value, substitute this equation, Leibniz equation. Then finally we are getting this value. If you simplify this, just you substitute these values in this Leibniz theorem, whatever we discussed this, substitute this, then finally we are getting this equation. Now from this equation, now see here, I mean this is our aim to find out what it is. That is our ultimate, that is our aim to find out what is the value of this. I mean that's what, see here, this, I mean in this equation, see here, this is our unknown value now, because w we know, w we already we have found it, but now we would like to find out u with respect, u is a function of x comma y here. That's what we are using here, Leibniz theorem here. Now when we are solving the Leibniz concept, then from that concept we are able to understand our dou u by dou x into dy. Finally we can obtain from this equation. Now just see here this equation, simplify this equation, 0 to integral of h dou u by dou x into dy. Then take this term into, I mean this term to the right hand side. Okay, this term only we would like to find out. Now 0 to dou by dou x into 0 to h minus u dy, minus this term it will come to here, then u into dh by dx. Now we have I mean now from this equation q we can get, now we have understood what is 0, the integral 0 to h dou u by dou x into dy, that value obtained from this Leibniz theorem. Okay, now I come to this, I mean now first I have considered the q equation first term. Now I'm going to concentrate in the second term now. Yeah, please. We complete it within 5 minutes. It's very simple. Now, second term. Now I'm going to consider this second term from this equation Q. Second term of this equation. Second term of this equation. Now, in second term, the equation's upper limit is h is constant with respect to y or z. With respect to y or z, h is constant. Then we can write, we can just, sign of the integration, differentiation can be interchanged. Then we are able to find out this second term of the equation. Then 0 to h dou w by dou z and dy is nothing but dou w by dou z into 0 to h w into dy. Now this is equation. Yes, we know. Yes is this value. This value we know. This value we know. From equation R. Then substitute R and S in the equation Q. Finally, we are going to get this is the equation. Okay, finally we are getting this equation. Now this is our final equation. Simplify this equation. Then this is dou by dou x into 0 to h u dy plus dou by dou z 0 to h w into dy. Now we have been derived already u and w. We have been derived under u and w. Sorry, u and w from that. Simply first I'm taking this term, substitute whatever we have found this equation. Velocity u value here we derived here, right? Substitute in this equation. Finally, u value. Similarly, then simplify this term, this equation t, the first term going to be simplified like this when you substitute u value. Then second term of this equation, t equation, we have derived already the value in terms of w. The value w already we derived. Then w substitute in this equation t. Then simplify this, the second term of this equation t. Substitute the value w value in the second term of the equation t. Then simplify this. You are going to get this. Then now, the equation t, we know the first term and second term. This is the first term of equation t. This is the second term. Sorry, this is the second term of the equation t, right? Then this is second term of equation t. This is the first term of equation t. Then sum it. Again substitute in the same equation. First term plus second term going to give this final equation. Now from this we obtain final equation, this one. Now with the help of this equation, with the help of this Reynolds concept, we can understand the bearing pressure with respect to velocity in x. The velocity of the lubricant fluid, with the velocity of the lubricant fluid in x and y and z direction, we are able to understand with respect to bearing pressure. Okay, so once we are going to discuss the problem, we can easily understand. Please, any doubt, please go ahead. Hello. Guys, any doubt?
No doubts.
Okay. Okay, shall we move to next concept?
Sir, time up.
What is time now?
2:45.
Okay, I think please go through your book. If we have any doubt about this derivation, anyway, derivation we are not going to ask in the exam, but you have to understand this derivation. Very, very important, because any competitive exam, if you are going for engineering service or any other competitive exam, descriptive type, this is one of the important questions. Please read it. If you are not understanding any steps, please bring into the next class. We will discuss. Doesn't matter. I hope that you might have been understood. But still, if you have any doubt, please, I'm kindly request you that bring into next class. No problem. Okay. So, but in general, finally, Reynolds equation help us to understand the thick film lubrication behavior. Thick film lubrication behavior in that sense, hydrodynamic lubrication behavior we able to understand with the help of the Reynolds equation. The fluid velocity, the lubricant velocity with respect to x and y, z direction, we able to understand with the help of the Reynolds equation with appropriate using this relation. Here the pressure is with the help of the bearing pressure. Here the pressure is function of x, y, and z. The velocity can easily evaluate, and we can easily evaluate in all directions. Velocity of the fluid element. Fluid element in that sense, which element we considered a lubricant element with respect to bearing pressure. Okay, guys. Yeah, please. I stop it here. I come to home screen. Please wait. Kalyan, only 59 students are there, Kalyan. I keep on telling that no improvement.
Uh, Sir, in Maharashtra and Jharkhand, internet services are stopped, sir. So
Oh,
that's why.
okay. Still, that problem is there. Huh?
Yes, sir. The yesterday and today, sir.
Oh, okay, okay. But because you are going to have exam, minor one, and on Friday, okay. And if the same problem will be continued, please you inform to faculty, me or the okay, because we are planning to conduct exam on Friday, minor.
Sir, minor keep on Thursday, sir, because on Friday people are traveling, sir, for writing gate exam. They have to go to their centers. So
I will try. You only suggested Friday. Last week also you told Friday. Now suddenly you are asking me that go back to Thursday. Okay, then I will discuss to Dr. Ismail and get back to you.
okay.
We try our level best. Otherwise, we can. What is the problem? Friday evening, na?
Uh, like students kept center in Warangal. Sir. They kept center in Warangal.
Okay, you ask the students Friday evening okay or not. Just you ask, discuss in your group and get back to me.
Uh,
Okay.
already discussed it, sir. And people are traveling, and there will be the people are traveling on that day. Sir. So
Mm-hmm. Okay. I will discuss with him and I will get back to you. Perhaps, I mean, if you are not able to do that Thursday, it will be Monday. But damn sure, we try to complete this week. Perhaps, unfortunately, unable to conduct, then we can go for Monday. But either Thursday or Monday, we will decide it. Okay.
okay, sir.
But please, guys, you prepare well. You prepare well in that sense. You think you make it your calendar Thursday exam minor Thursday evening. Okay.
Okay, sir.
Okay. Thank you, guys.
Thank you.
Thank you, sir.
Yeah, thank you, Pa. Thank you.